Good evening, Ritika.
Good evening, ma'am.
So, have you done anything in your hydrocarbon chapter till now? Any questions from that?
No, ma'am.
You did anything or not? Which chapter is going on in your school nowadays?
Thermodynamics, ma'am.
Okay. Till what time your teacher has come to? Ritika, have they just
Ma'am,
started?
she finished first law, ma'am.
Okay. You're finding any difficulty into it?
No, ma'am.
Okay. So in the last class, we discussed a few things about the journal terminologies. And and we discussed what is work done. We discussed what is internal energy, what are state variables, what are path variables. Now we will be learning about heat. The reason why I was trying to ask you something is that since the exams are coming, if there is something uh, which you want to do it quickly or at first place, you can let me know and we can probably switch on to that one first. Anything which is coming to your mind, which you want to do it before thermo or some topic of a thermo or equilibrium?
No, ma'am.
Okay, so let's begin. We'll be talking about heat. See, initially there will be a lot of definitions and concepts. There are questions or rather numericals in thermodynamics, but they are pretty conceptual. If you are clear about the concepts, only then you can do the question. Because here you will see you have to put the values with the sign, the plus sign or the minus sign, right? So the plus and the minus sign can be given to any species or anything only when you know them, how to put them, right? So talking about heat, so the definition is on the screen that it is the energy that flows across the boundaries. Like suppose if I have this glass of water, the glass of water is cold. If I am touching it with my fingers, the energy will be transferred from my hand to this glass, right? But if I take a cup filled with hot coffee, what will happen? This is hotter than my hand. As a result, the heat will flow from this to my body. So that is, and the cup or the mug, the walls of this container will be acting as, or they act as a boundary between the system and the surrounding. My hand is a surrounding and they are the system. So that is the technical definition of heat, that it is the energy which flows across the boundary of a system during a change in state by virtue of difference in temperature between the system and the surrounding. It looks a bit difficult and it has got so many technical words, but the key point is that heat or energy will always flow. It will always be flowing from the higher temperature to the lower temperature. This is something which we must remember. That is, as the water flows from the highest place in the, what we call it as ladder, to the lower, it will never flow backwards, right? So similarly, the heat will flow from the higher to the lower temperature, right? Then the next formula, the formula written here is, as I mentioned, this is the key takeaway. It is always be from higher to a point of a lower temperature. Then heat absorbed or evolved will be given by or is given by the formula Q is equal to ms delta T. This is an important concept, or it is important formula. In the physics practical, you might have been asked to determine it in a practical laboratory, right? So here M is the mass of the substance, S is the specific heat, and the T is temperature difference, right? That how much hot or how much cold the substance is, right? If heat flows, as I told you, please note these points here. If heat is given out by the system or heat is coming into the system, right? Endothermic, heat is absorbed, represented by plus sign. Heat given out, it is negative sign. Please note it down quickly, Ritika. Moving on to the next one. What are the units of heat and work? We might have done it, but I'm not too sure. Have we done it, Ritika, or not?
No, ma'am.
Okay. The units are important. As you know that whenever you are solving a numerical, the units have to be proper, right? So in this case also, we must have a proper unit. So work and heat, they will have the same units, right? What is the definition of a calorie? That is the unit of or rather, what is how much amount heat is required. The unit of heat is calorie, which is very often used. I believe you understand MKS and CGS systems. Calorie is a CGS systems unit, whereas joules is MKS system, right? Have you heard about these two systems, CGS and MKS?
Yes, ma'am.
This is MKS and the calorie is a CGS system, right? So 1 calorie is defined as the amount, as the quantity of heat required to raise the temperature of 1 gram of water by 1 degree. You will take 1 gram of water and increase its temperature by 1 degree. That can be 3 to 4 degrees centigrade or 300 to 301 degrees centigrade, right? So you just have to increase the temperature of the water by 1 degree centigrade, right? Then we say 1 liter atmospheric will be equal to 101.3 joules or this many ergs or this many calories. Please note down these conversions. They are very useful or they are required in the exams, not given in the book. So I insist, please note them down. I think internal energy we have covered or not, Ritika, in the last class. Okay, I'm not getting any response from you, Ritika. Please reply whether we have covered internal energy in the last class or not.
No, ma'am.
Okay, Have you done the assignment? I think I gave an assignment to the team to send it to the students. Have you done that assignment? Okay. Now, what is internal energy? That is the next thing which we must understand. The energy possessed by the system. Like I am a system, you are a system. We possess many type of energies, right? One energy is because of the food we have taken in. The another type of energy can be because of the our internal organs. Each of the organs also must be having certain energy, right? There must be air filled inside our body that will again be providing certain energy to it. Similarly, every system that can be an atom or a molecule has many different types of internal or many types of energies, and sum of all of them is referred as internal energy. Now, internal or the other name of this energy is called as intrinsic energy, right? So what are these energies in a system? The atom is made up of mainly proton, electron, and neutron. Now, what they can do? They can rotate on their axis. They can do the vibrational motion. I believe you understand the vibrational motion. That is a pendulum-like motion. If this is a pendulum, it will move in one direction to the maximum distance, come back to the center position, move to the next side to the highest distance, and come back to the center. This is rotational, vibrational motion, right? They can rotate on their spin. Then they can have a electronic energy. You must understand the proton are going to repel each other. Electron, they are also going to repel each other. But a proton and the electron are going to attract each other. So what are they? They are also different types of energy. So if we come to know about the values of each one of them, like if somebody tells me inside me what energy I have energy because of air, X grams or X joules rather, right? Because of the food I have taken it is, let's say, Y joules, right? Because of the other factors, it is Z. So the total energy possessed by me will be X plus Y plus Z. Similarly, the total energy possessed by a system will be equal to the sum of all these 4-5 types of or more than that type of energies. Now, we say this is a very important statement, Ritika, that we cannot find the absolute value of internal energy. Now, what is the meaning of this statement? Absolute value means that if I say that this is 1 kiloliter or 1 liter of water, it contains 1000 joules of energy because we have measured it. But it is not possible to do so with the systems. Why? Absolute values can be understood or found only when only one thing is taking place at one time. I think in terms of Earth, it will be a bit easier for us to understand that Earth is always moving on its axis and it is moving around the sun like this, right? The absolute speed of both of them can never be measured. Why? For knowing that one motion has to stop, but that is not possible, right? So we say the Earth is rotating at this speed. We can give a general statement, but we cannot get a specific whether it is 300 kilometers per hour or 3000 kilometers per hour. Similarly, if a proton is repelling the other proton at that particular time, it must stop repelling the other, or rather it must stop attracting the other electron, right? So that is why we are not able to find the absolute value, right? But we can always find a change in internal energy, right? Like for Earth, we say it has moved from this place to this place. Distance upon speed will tell you the time taken, right? Similarly, we do that thing that we measure the change. Measure the change means change can be 300 minus 600. That is giving you the answer as minus 500. It can be 600 minus 900. Again, the change will be of 300 units. So that is important question. Why it is not possible to find the absolute value of internal energy, right? So the answer is also given in front of you. So, and the formula is also given for you to remember and use, that change in internal energy will be equal to E2 minus E1. Now, E2 is the internal energy of the product or the final state, and E1 is the internal energy of the reactants, right? Most of the questions, either of the two values are given, only the units may not be that proper. They may be, one may be in CGS, other may be with MKS system, right? So quickly note down the formula before we move ahead. Now, what is enthalpy? Enthalpy is said to be the total heat content of a system, the total amount of heat present into it. For that, let me find a ball for you. Now, this is a ball and it is having certain amount of energy because of the content it has inside. That is, it may be made up of solids, various type of particles must be stuffed inside it. And because of these particles, it certainly possesses internal energy. Now, what I'm going to do here is, I'm going to apply a certain pressure on it, right? The moment you apply pressure on it, I believe you can see the depressions. You are applying pressure, right? So here it is written that the total energy will be what? The internal energy it was having and the energy it has got because of me applying pressure on it. That is pressure into volume. When you apply pressure on it, you can see its shape deforms, right? So the total energy of the system will now be known as enthalpy and will be represented by H, and this will be equal to E, that is internal energy, plus work done or PV energy, right? As we have the formula for internal energy, we have the formula for enthalpy also. If we cannot measure the absolute value of internal energy, we cannot measure the absolute value of the enthalpy also, right? So it will be, again, as I told you there, it will be delta H is equal to H2 minus H1, or we can say delta H is equal to HP minus HR, right? So Ritika, quickly note down, take a minute, think about it, whether you have understood it or not. Let me know if anything is not clear. Note it down quickly. Now, we will learn this formula, which tells us what is the relationship between the enthalpy and internal energy, right? Since the derivation is in your syllabus, I've also tried to put it like that, right? You must be having mathematics in your syllabus, so it will be pretty easy for you to understand it, right? For the changes, I'll tell you for the entire chapter of thermodynamics, we'll always be talking about the product minus reactant, right? So for this, we have taken a reaction in which a chemical reaction precisely, in which X has changed into Y, right? So what will be the value of delta H? As I told you, HP minus HR. In this case, it will be HY minus HX. Then we know that the formula of H is equal to E plus PV. As they were connected, that is the reason I'm asking you always to note them down, right? So what you will get? You will get the equation as by substituting the value. E and PV value, you will be substituting them. And then you will come to you can see the derivation. I don't think there is a need for me to explain each and every step to you. Is all the steps clear to you, Ritika?
Yes, ma'am.
Just wait. Bolo beta. So note down this derivation quickly. I think you are done with it.
Yes, ma'am.
Now then we will be talking about what is the first law of thermodynamics. Before we study about them, please remember, for thermodynamics, we do not have laws, we do not have any proofs. Like you have equation of motion in physics. We have small g, capital G formula in physics, right? In chemistry, we have many derivations. But for the laws of thermodynamics, we do not have any proof for that. But the question arises why they are so popular and why do we study in the syllabus? The reason is simple. We say that there is nothing contrary or nothing which is contradicting to them is known to us, right? Whatever we know is from our understanding and we know everything is correct. We do not have anything against them, right? So that is the beauty of these laws, that nothing contrary to them is known, right? So the first law states to us that energy can neither be created nor destroyed, right? But if one form changes into another, like I have just taken a small amount of coffee and now I'm speaking. What is happening? I have taken energy in the form of a food and that is now being converted into sound energy, right? So that's how we say that if you take a battery, put it in a remote, what happens? The chemical energy is converted into, let's say, electrical energy because signals are said to be electrical, right? So according to the first law of thermodynamics, energy can neither be created nor destroyed, right? It should be pretty easy for you to remember. Now, coming to the next, what we have to learn? We have to understand this is, again, this is the justification for the first law of thermodynamics, very popular or very frequently asked questions in the internal exams, right? That how do we get to know that this is the first law of thermodynamics, or how do we show that it is true? Again, I'm saying it is not a proof. Whatever has happens, and we are just putting it in a form of a expression, right? So what we are saying, just read the question, read the statement carefully. Or let's take an example from the day-to-day life. You have, let's say, 1 liter of water and you have started boiling it. Once it is boiled completely, once you started boiling, there must be a certain amount of energy it was having. Now, what has happened? After heating, after rather boiling, now its energy has changed to from E1 to E2. Now, what is this E2? Energy, whatever it was having earlier, plus the amount of heat or work you have done on this, right? So the statement is written as that E2, that is the final energy. In this case, the energy of the heated content, right? That is E2 will be equal to E1 plus Q plus W. That is the amount of heat you have supplied and amount of the work you have done. Like if you have seen that if you are boiling water in a closed container, the lid start uplifting itself and it creates a noise, right? So that's what we say it will be, that is what it is doing work. It is lifting, coming down, coming up, coming down, coming up, coming down. It keeps on doing so, right? So that is E2 is equal to E1 plus Q plus W. Then if you rearrange it, and so what you get? E2 minus E1 will be equal to Q plus W, or we can say delta E will be equal to Q plus W, right? Now, as I have told you on this question, on this particular very basics formula, you get many questions. What you have to do? You have to be smart enough to use the value of W with the proper sign, right? So therefore, I have taken a hypothetical case saying that Q is the heat absorbed. Water has absorbed the heat, right? And work is done by the system. Done by the system means the system, that is water itself, is expanding, right? So work done by the system is positive, right? And or rather heat absorbed by the system is positive, work done by the system is negative. So when we substitute these value, we get delta E is equal to Q minus W, right? So that is the reason it is important for us to learn by heart when Q will be positive, when W will be negative, when W will be positive. Only then we will be able to do the questions correctly. So the lines which I have put in the color with the marker, please note down them. And the other thing that this one, just note down these things. I'm not asking to write down whole of them because it will take a lot of time. Number one. Number two, it is not that required. Okay. Moving on to the different examples of it. How we have to solve the questions very carefully, Ritika. We'll be, see, this is a very common mistake. Therefore, I wish to emphasize on these points only. Although you know that the formula is pretty simple. It can be delta is equal to Q plus W, or it can be Q minus W. And if you put everything with the sign, there can be a mistake. And this is the purpose we did the terminologies in the first class. So the first one, let's take the first. I will not take the all of them. I have just picked up maximum, I'll say 4 or maybe 5. You have to read the question carefully to solve such numericals. When we say that ideal gas undergoing a isothermal. Isothermal means they'll change, the internal energy of the system does not change. Remember, we did it in the first class or last Wednesday class, right? When delta H is 0, delta E is also 0, right? So the formula was delta E is equal to Q plus 0, Q plus W. I'm so sorry. So when you substitute this value for isothermal systems, you have to read the questions very, very carefully, Ritika, right? If it is saying isothermal question, that means we must remember in an isothermal system or isothermal change, delta E is 0. So in that formula which I have asked you to write, that was the purpose. Delta E is equal to Q plus W. If you substitute the value of delta E is equal to 0, you get Q is equal to minus W, right? I believe it is making sense, or you can change the signs. After that, it is your baby. You can play with it anytime. More you do the practice, more you will be comfortable in it, right? Now, is the first condition clear, Ritika, so that I move to the next one?
Yes, ma'am.
Okay, moving to the second condition, where we are saying isochoric. Isochoric, I told you in the last class, was that the volume is 0. Rather, change in volume is 0, right? So when the change in volume is 0, that means no work is done, that the volume has remained same. That if you are boiling a water in a closed container, volume is fixed, right? So that means delta work done will be 0 and delta E will be equal to Q. Again, you may be saying that I'm saying many a times, but it is important. 1 mark, MCQ, anywhere this can be asked, but you just have to read the question carefully, right? That is the second condition. Now, then the third condition. What is the third condition? We will talk about the adiabatic systems. In the adiabatic system, heat is not exchanged between the system and surrounding, right? So again, this time what happens? Q becomes 0. So delta E will be equal to W, right? That is change in internal energy, change in enthalpy rather will become W. Again, you will understand that W can have a positive as well as the negative sign, which is written here. Don't leave this point that you have to put the you have to solve all the thermo questions with the help of the sign. The sign is not correct, then the answer is also not correct. I believe, I'm not too sure, earlier it used to be in the physics syllabus of light. 1 upon F is equal to 1 upon V minus 1 upon V minus 1 upon U or something was there. Then the distance between focal length to this is positive, the other one is negative. So same type of a concept we have to apply here. We have to use the signs very carefully. Coming to the next condition. Gas is expanding, right? That is, you are heating a gas in the container. It was a 5-liter flask. You have only 1 liter gas filled in it. Now it is expanding and the entire flask is filled, right? So what will happen? Expansion is taking place, right? So if a gas, the condition number 4, that is if a gas is expanding against the external pressure. There is always atmospheric pressure. So we are expanding a gas, expanding the gas against the external pressure, right? So work is done by the system. W will be equal to minus P delta V. Substituting the values, we will get delta E is equal to QV because V is 0, right? If the work is done at a constant volume, we'll see if what happens if we are doing is constant pressure. P delta V, and delta V we have, so what we have said delta V becomes 0. Change in volume remains same. There is no change in the volume. This is an important conclusion. Delta E is equal to QV at constant if any work is done or expansion is done at constant volume, right? Coming to the next condition. See, as I told you, Ritika, please note down the last thing. Delta E is equal to QV, because in the next slide we are going to learn delta H is equal to QP. This is heat supplied at constant pressure, right? Heat supplied or heat absorbed, both, it can be both. So the change in internal energy is equal to, that's how we read it as. Change in internal energy is equal to the heat absorbed or heat evolved at constant volume. The last two lines are very, very important for solving the multiple choice question, Ritika. Okay, coming to the next formula, which will be, I will be writing it here so that you can put it on the same page or same place rather, I was about to say. That will be delta H is equal to QP, right? Change in internal energy will be equal to QV. Change in heat, I'm using the term change in heat, which can be absorbed or evolved. And then in the next slide, we will see that delta H is equal to QP. Derivation is not important for you, Ritika. You just note down the two formulas and practice them as and when the question arises in your book. We have to use these two formula. QP is equal to QV plus delta NGRT. Now I will write what is NG. If you have done that electrochemistry chapter in your school, you may be knowing this. Delta NG means number of gaseous products minus number of gaseous reactants. At times we say that as NPG. NRG. This is important, right? Like for example, we have PCl5 dissociating to give us PCl3 and Cl2. This is gas, this is also gas, and this is also gas. So delta Ng will be equal to 2 minus 1, that is 1, right? If anything is solid, then that won't be counted. I'm just teaching you this because I'm not too sure whether you have been taught about this in equilibrium or not. Suppose we have calcium carbonate, which is solid. It dissociates into calcium oxide solid plus CO2 gaseous. So delta Ng in this case will be, on product side we have 1, on reactant side we have 0. So this is 1 minus 0, again 1, right? If you take it for ammonia, production of ammonia, N2 plus 3H2 gives us, let's say, twice ammonia as per the balanced chemical reaction. So delta Ng will be equal to 2 minus 1 plus 3, right? So that will be minus 2. Quickly note them down, Ritika, for your clarity. Please note down all the examples. It will help you in equilibrium also. Okay. Then heat capacity and specific heat capacity, they are important from the perspective of define the following terms, right? So please just note down the first definition. It is the amount of heat required to raise the temperature of a system by 1 degree. System can be a very small thing, a system can be a very big thing, maybe like the entire earth can be a system. So just note down the first point and the units of it, right? Rest of the formula, we will not go into details. That is not required. Okay, I believe you have done it. Then again, specific heat is important for us from the perspective of the definition. Calorimetry or specific heat experiment. Do you perform these experiments in your laboratory, Ritika? Maybe in physics or chemistry?
Ma'am?
Calorimetry. Have you heard about the name of bomb calorimeter?
Yes, ma'am.
Have you performed the experiment in the lab?
No, ma'am, we still haven't done it.
Okay. So bomb calorimeter is used to find out the specific heat of the various substances, various metals, I believe, right? So what is the specific heat? Again, it is important from the perspective of a 1 mark question. That is, it is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree, right? Again, you have become specific, 1 gram of a substance by 1 degree centigrade, right? Again, its unit are also important. There we have done the specific heat of water, and this is specific heat in general, right? Quickly note down, Ritika. Okay. This, I think we have already understood what is an isothermal expansion. Delta E will be 0. The conclusions we have done. So there is no point in repeating this again. We have already done it, right? We need to do this formula. We need to again, this is more of a burden, it looks like, for Hithika to write down the formulas. I'll appreciate if you can do some questions as per the school's requirement, because many schools, as I have discussed with other students, not from learning room, from other states as well as the schools, they say that some of the teachers have not taught thermo at all. If they have taught, they have taken up the selected portions only, right? So I cannot be too sure what is to be emphasized, what is not to be emphasized like that. So I'm just giving you the formulas. In the next class or anytime if you come back to me that you need more practice on it, I'll be happy to help you. You note down please another formula, that is PV is equal to nRT. P, as you know, is the pressure, V is the volume, N is equal to number of moles, and R is gas constant, and temperature, T is temperature. Importantly, it has to be put in Kelvin, right? Then if you have to find out the work done in reversible process, then we will be using this two formula, right? If you are doing it at constant pressure, then we will be using the formula P, this one. Otherwise, we will be using this formula. From the formula PV is equal to nRT, I believe, Ritika, you can easily make it out that P and V are inversely related. If you increase the pressure, the volume will decrease, right? Okay, I believe you must have noted down. Then we talk about what is thermochemistry. We can call it as chemical energetics. I prefer to call it as chemical energetics. Most of the time we write the reactions, but we do not write the physical state of the reactant. We do not mention how much heat is absorbed or how much amount of heat has been taken out from this system, right? So whenever you are writing a reaction in which you are mentioning the change in temperature, then that is called as thermochemical reaction. And the branch of chemistry which deals with it is called as thermochemistry. Now, below that, I have put up a perspective because this is a very common derivation. Derivation not in the sense of that how do you derive it. Derivation means drawing the conclusion, as I want to tell you. That how to draw that conclusion, whether the heat is absorbed or heat is given out. And if heat is absorbed, what does it mean? And if heat is given out, what does it mean? So to clarify that, I have taken a first of all an exothermic process, or you can take up the first reaction. As I have said it here, physico-chemical changes are classified as endothermic, and which are accompanied endothermic process. End means you're taking it. X means you're taking it out, right? Now for the endothermic processes, as you can see, the first two reactions, look at them carefully. What I have done, in the first reaction, the heat is given out. In the second reaction, what I have done, reactant and products have exchanged their positions, right? As a result, the amount of heat which was being actually given out now is being absorbed, right? So the other perspective which I was trying to tell you, if heat is given out. That means HR is greater than HP, right? Constant pressure, constant volume. We mean to say, do you realize that at whether we are cooking food, whether we are conducting any chemical reaction in the laboratory, are they done at constant pressure or constant volume, Ritika? Any answers, Ritika? What remains constant around us? We say when we are living in planes, you say that the pressure is constant, it is around 1 atmosphere. As you go to sea down, the pressure changes. As you go up on the mountains, or if you travel by aeroplane, the pressure increases, right? Wherever we are conducting a chemical reaction or cooking food in a kitchen, what we are doing? We are doing the reactions at constant pressure. Pressure is constant, it will remain one atmosphere. You're boiling milk, you're cooking vegetable, you're not bothered about the volume. If you have to boil 1 liter of milk, you can take a exact 1 liter wala uh, container, or 2 liter wala will also serve the same purpose, except for the fact that 2 liter if you are boiling 1 liter milk in a 2 liter container, you'll be wasting heat. Why? Because first of all, whatever fuel you are using, a gas burner or the what we call it as coal or whatever fuel you are using, what will happen? That will be first of all used to heat the container. The steel utensil will be heated up. And if you have to heat the 2 liter container, oh my God, it will be wasting a lot of energy, right? So that is important for us to understand. This is again a very important question, which is very often asked, right? That we usually take up the reactions at constant pressure, whether in lab or in day-to-day life. This is we have already done that what is delta E is equal, E will be QV if volume is kept constant, and if pressure is kept constant, we will get delta H is equal to QP. These are the two conditions which are important for us to understand and remember. Please note down, Ritika, that chemical reactions in lab, we work at constant pressure. All right. At times, if you are interested, you may check the results of the same experiment conducted. And if you have heard, like you may be able to guess that today I'm sitting at a temperature which is approximately 1 degree centigrade. So therefore, I have to put off a lot of woolens. I have to wear hand gloves. I was wearing my cap also. I am not wearing my cap, so my ears are numb now. I need to put on a heater. So what I'm trying to say is, if you are conducting an experiment at your laboratory, right, in Chennai or wherever you are there, I believe you are in some part of southern India. There, if you are conducting an experiment, and if I'm conducting an experiment here, the qualitative results will be same, but the quantitative results will be different because the temperature and pressure are changing, right? Then this is an important formula. I believe if you have already written, then fine. Else, please note down this formula. So let's move on. What is a standard state? Now, a very common or very often given example is that to understand the capacity of each and every student, to find out whether he or she has learned the concept completely or not, what we do, we usually or we 100% give them the same test under the same conditions, right? We say, okay, tomorrow you will be having a 30-mark chemistry test from thermodynamics. Similarly, whenever we are doing the thermochemical reactions, we must standardize certain things, right? And what are those things? Those things are that we must take everything in its standard state. And that simply means that, look at the last line carefully, a pressure of 1 atmosphere and constant temperature is taken as standard state. Whatever is the physical state of a substance under this condition, right? Whenever you are doing the calculations involving heat of reaction, we must take the standard state of every substance. That can be element, compound, or a mixture, right? That we will be taking it as 1 at 1 atmospheric and at the room temperature. So for example, we say that coal, diamond, graphite, all of them are different forms of carbon. Can you predict what is the standard state of carbon? Out of these three, which is the standard state of carbon? The standard state of carbon is diamond. It's not coal, it's not graphite, right? And please understand, the energy contents of coal, diamond, and graphite are different. Why? Because for diamond and graphite, if you go back to your class 10th, you will realize the diamond and graphite both were having different structure. One was having tetrahedral and graphite was having a layered, hexagonal layered structure which was slippery in nature, right? So that is about the what is a standard state, right? And there can be many numericals based on this. Do you have any idea, Ritika, that what is there in your store? Where store means your school. What is there in store in your examination? Whether they teach, you are expecting numericals from this chapter, you are expecting theoretical concepts from this chapter. Has your teacher given you any clarity about it, Ritika?
No, ma'am.
Okay. So these are the certain definitions which may which may help you in understanding the concept as well as solving the numericals. They may ask you define what are the different allotropic forms, right? As you can see, I would like to focus on this. In this particular section, it is when you convert diamond to amorphous form. I believe you understand the meaning of the amorphous as well as the crystalline forms. The amorphous forms do not have a proper, what you say, the position of the atoms there, right? Whereas the crystalline forms do have. You can see the conversion of crystalline form into amorphous form. You have to supply a certain amount of energy into it. Need not to write that, but just give me a minute. It is known as energy of transition, right? That is amount of energy required to convert. Please remember, for any thermochemical equation definition, process definition, we will be using the word 1 mole of a substance. Why I have written 12 grams here? That is 12 gram means 1 mole. Do you remember that relationship? 1 mole is equal to atomic mass in grams, and which is equal to 6.022 into 10 to the power 23 is equal to 22.4 liters, right? So whenever we are describing enthalpy of solution, what you have to say? Energy changes accompanying when 1 mole of a substance is completely dissolved in excess of solvent. It is important to say excess of solvent. When I'm saying enthalpy of transition, amount of energy exchanged, I will neither say absorbed or evolved because anything can happen here. Unless or until I'm given a specific example, I'll be playing safe, giving the technically correct definition by saying, please note it down, Ritika, as I'm saying, it is the amount of energy exchanged when 1 mole of a substance changes from one allotropic form to the other allotropic form, right? So moving on, we will see what else we have to cover today. This is a very, very theoretical part, which we will definitely not cover in case. See, integration to me should not be asked to you, right? Reason being, chemistry is a subject which is taken up by the bio students as well as the mathematics students. Bio students will not be able to do this integration. So since last 2-3 years, they are thinking of removing the derivations from it and they haven't asked. Earlier, they used to ask the derivation from this section. Especially we have a chapter called as chemical kinetics in class 12. There, that is full of such derivations. So that is why if it is being taught to you, then we can also go ahead with it. Moving on, as I told you that there is the reactions are, or rather the definitions are also important to us in the thermochemistry part of it. So standard enthalpy of formation. I have told you what is enthalpy of formation, right? Let me write it down for you. So then probably you will be encouraged to understand and write about it. I'll tell you the difference just to make your life bit easier. If I'm writing enthalpy of formation, I'll be saying it is the amount of energy exchanged. Again, as I told you, I'll be smart not to write absorbed or evolved. Energy exchanged when 1 mole of a substance is formed from its constituents. But if somebody asks me to write the definition of enthalpy, or rather, sorry, asks me to put up the definition of standard enthalpy of formation. I will be writing everything as it is. And in the end, its constituents, after the word of its constituents, I'll be writing in there, that is at this place, I'll be writing in their standard state. if I have, for example, if I have to write the equation for the enthalpy of formation of carbon dioxide, carbon dioxide will be formed from carbon and oxygen to give us CO2. Now, what will be the standard state? A standard state of carbon dioxide, I said, standard state means physical state at room temperature. At room temperature, what is the physical state of carbon dioxide, Ritika? Come on, Ritika, you know this.
Solid?
Carbon dioxide as is CO2 at room temperature is solid or liquid or gas. We breathe in oxygen, we give out carbon dioxide. So what will be the physical state of carbon dioxide? It is a gas. And what is the physical state of oxygen, Ritika, at room temperature? Oxygen is also gas at room temperature. Water is liquid. The standard state of water is liquid. Carbon, as I have told you, it is graphite. Right? So if I have to write the standard enthalpy of formation, I'll be writing the equation like this. Carbon in the form of a graphite, oxygen as a gas, carbon dioxide as a gas, and whatever the value of delta H is, that has to be mentioned here. Right? If I take carbon in any form, like if I say carbon as a coal, right? And if I write it as carbon, coal, reacting it with oxygen gas to give us CO2 gas. So that will be only the enthalpy of formation. That won't be the standard enthalpy of formation. That is the difference between the two. We just need to remember these technical words, right? Because I believe that there won't be a numerical for you this time in this chapter, but, or in this section rather. There won't be a numerical, but differences can be asked. Then, which of the following is not a standard enthalpy of carbon? Or which of the following is a standard enthalpy of carbon can be asked to you, Ritika. Right? Then they say that numerically, if you are solving the numerical, then it is important enthalpies of free elements in their standard state is 0. Now, what does that mean? That simply means if I am solving a numerical, oxygen exists in nature as O2. If I'm solving a numerical, I'm writing H2 gas plus O2 gas gives us water liquid, right? So first thing is we need to balance this equation by writing 2 here and writing 2 here. Heat of formation of hydrogen will be taken as 0. Oxygen will also be 0 because they are in their standard state, right? For water, there must be a certain value given to us. Similarly, for sodium, it will be 0. For chlorine, it will be 0, right? I believe it is somewhat clear to you, Ritika. This will be much more clearer in the next class when we solve the numericals or your teacher gives you an opportunity to solve the numericals, right? Okay, or let us solve the question. If I can find one. No, I don't have. We'll be doing it in the next class. Then this information is important. I have told you what is enthalpy of formation, what is standard enthalpy of formation. Then I have told you the enthalpies of free elements in their standard states are assumed to be zero. There is a difference between being zero and assumed to be zero. For doing a certain calculation, we assume them to be zero, right? So as to make our the complex calculations bit simpler. We assume them to be zero, right? Now then you please note down this formula, Ritika. Quickly note down so that we can cover at least one or two more definitions before we end the class.
Noted, ma'am.
Okay. Now, enthalpy or heat of combustion. What is the meaning of this? For that, we must understand what is combustion. Combustion means heating anything in excess of oxygen so as to get carbon dioxide and water. This is, I think you remember we have done it in alkenes and alkanes also. Combustion means heating anything in excess of air or oxygen so as to get carbon dioxide and water, right? So again, what will be the definition? Amount of, see, here I have written as the amount of heat evolved or decreased. You can say the heat exchange when 1 mole of a substance is completely oxidized or converted into carbon dioxide and water. Believe me, these definitions, except for heat of neutralization, all of them will be moving like this, that you need to know the process, right? What is heat of, what is combustion, and then combine the words as I have told you. I believe you can do it now, right? You can write it at your own. Clear?
Yes, ma'am.
Okay. Then enthalpy or heat of solution. Again, what is the process? You are dissolving a known quantity of a solute, that is 1 mole of a solute in excess of the solvent. That is the process of formation of solution, or this is the process of dissolution, right? Dissolving or dissolution. So what we say, it is the heat exchanged when 1 mole of a solute is dissolved in excess of the solvent, right? I believe it makes sense. This is heat of solution. Then we talk about heat of dilution. Heat of dilution means when 1 mole of a substance is diluted from one concentrated form to the another form. Like if I have a 1 molar solution, like last evening when I cooked something, the salt was in excess. What I have to do? I have to put some water into it. What I'm doing? I'm diluting it, right? That is, I'm decreasing the concentration of the reactant per unit volume. Although I'm talking, but I'm doing a part of a physical sciences, right? So what is dilution? That when you dilute 1 mole of a solute, right? If there was a solution, that is again total amount of heat exchange when 1 mole of a solute is diluted from one concentration to the another. Like as I gave you the example, there was excess of salt. I have diluted it in such a way that it becomes what we usually consume, right? So you are converting one concentration to the other concentration, right? You are not saying that you are making it as zero. Then, as I told you, the heat of neutralization, that is a bit different in the definition. We will say it is the one, instead of 1 mole, we will be focusing, or we will be exchanging that word 1 mole of a substance to 1 gram equivalent. The amount of heat evolved when 1 gram equivalent of an acid is completely neutralized by base, or vice versa. Right? 1 gram equivalent. We are not saying 1 mole, right? Now, gram equivalent is a different concept. Let me see. I believe your teacher has not reached to this concept as of now, isn't it?
Yes, ma'am.
Okay. So acid and base react to put up or to form salt and water. This reaction is called as neutralization. So how do we define it? We say it is the amount of heat exchanged when 1 gram equivalent of an acid is completely neutralized by 1 gram equivalent of a base, right? This is heat of neutralization. Gram equivalent, I'm pretty sure that nobody is going to teach you, or they are going to ask you. You can check with your teacher. If they say, okay, they will be asking, I'll be teaching you, right? The important thing from this or the question which is theoretically asked for this question, this section or this concept is the heat of neutralization of a strong acid by strong base is a constant. This is again an important question, Ritika, which is being asked many a times. They give us this statement and then say why. Heat of neutralization of strong acid and strong base is 13.7 kilocalories or 57 kilojoules. Remember, as I told you, when we talk about thermo, we talk about the units. We talk about heat given out or absorbed. Why it happens, let us understand. Let's say if I am reacting HCl with NaOH and getting NaCl and water. What is happening? In this case, H plus will dissociate as, HCl will dissociate as H plus and Cl ion. NaOH will dissociate as Na plus and OH minus ion. And what they are going to do? They, Cl and Na, they will react to give us NaCl. Water will be formed like this. Now, basically, what is this reaction? H plus and OH minus reacting to give us water. They are 100% dissociated. Strong electrolytes, I'm again not very sure whether you have been taught about the concept of weak and strong electrolyte. Do you know what is a weak and strong electrolyte, Ritika? See, again, I'll say, please remember this list of strong and weak. This will help you in understanding or clearing or doing the questions of equilibrium also. For weak one, we say the examples are only this: ammonium hydroxide and acetic acid. Whatever else is there in your book, at times we can use H2S here also. Rest of everything is strong. HCl, HNO3, NaOH, H2SO4, KOH, all of them are strong. And strong means they dissociate 100%. Whereas for weak, we say maximum dissociation is of 3%, right? So when, please note it down. I'm giving you a minute, Ritika, quickly.
Done, ma'am.
Okay, good. So why this value is constant is that HCl and NaOH, they will dissociate 100%. So if I have taken 100 molecules, I'll get 100 H plus here. And here I will get 100, 100 H plus. And we will get 100 Cl minus. We'll get 100 Na plus and 100 OH minus. Now this reaction of this and this will be 100% complete. Whereas the 100 H plus and 100 OH, they will hardly react because I said they will hardly be reacting to 3%. So that is the reason they are completely doing it. So the value remains the same. It will be, we put it this way, that it is in fact heat of formation of water, which will always have the same value, that is of 13.7 calories, rather kilocalories, right? So this is one of the important reasoning questions which may be asked to you. And as you can see, this heat can be, you can do it in practical lab also. But what happens at many a times is the amount of heat absorbed is too less. Whatever thermometer which we are using at home to measure our temperatures, which is, let's say we say 101.2 is the temperature. And there must be many minute lines in between them, right? So let's not go into that details, but just to tell you that in the laboratory, we use a bigger, almost like your hand's length, that is Beckman's thermometer, which can measure the heat in terms of 0.0101.003 tak it can measure, right? So with the help of that, we can find out these things. Then we will be talking about these things. Enthalpy. Do you understand what is the fusion process, Ritika?
Yes, ma'am.
Yeah, what is that? I didn't hear. You said yes, I believe. Phase transition means that's it. We are talking about now about the physical changes. Fusion means solid is changing into liquid. Now, this process is melting. So in the definition, that word has to be given its importance. It is the amount of energy exchange when 1 mole of a solid changes into liquid at its melting point, right? Then vaporization, when 1 mole of a liquid is changed into vapors at its boiling point, because vaporization is conversion of liquid into vapors. Then sublimation. Sublimation means solid is changing into vapors even at room temperature. So amount of energy exchange when 1 mole of a solid is changed into vapor state below its melting point, right? Then heat of atomization, amount of heat required when 1 mole of a substance is 1 mole of an atoms are converted into their gaseous state, right? So we have today covered the basic definitions, and we'll try to catch up, do at least one or maximum one or two, because we have to cover a lot of syllabus. I'll be trying to clear the concept through the questions and making you the importance or making you do the some questions. You want to have an assignment on today's class, Ritika, or not?
Yes, ma'am.
Okay, have you done the previous one? No? No issues, but please do it. If one or two topics or one or two terminologies were not taught to you in the last class, they are clear now. So that will help you in your final exams, Ritika. Right? Any doubts from today's class?
No, ma'am.
Okay, then see you on next Monday. Have a good day, Ritika.
Thank you, ma'am.
Welcome.